Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to thermal properties of materials on material science and engineering. So far we have discussed in the previous video related to gas laws and the ideal gas equation. So in this video we are going to discuss about another important concept which is related to the change of state of material, particularly water, okay, and related to thermometry, which is one of the most important concepts related to thermal science and thermal engineering, thermal properties. So we are going to discuss about triple point of water. Okay, so before discussing that, just a quick recap of what we discussed in the change of state. We all know every substance, every material, it exists in three possible states: solid, liquid, and gas or vapor. And any state of a substance can be changed into another by heating or cooling it. That is, either by supplying heat or taking heat away from it. And the transition of a substance from one state to another, that is called as change of state. Now, here we are discussing about triple point of water. So, we know that the three possible states of water, they are ice, the solid state, water, that is the liquid state, and water vapor, which is the gaseous or vapor state. Okay, ice to water to vapor. So the common change of state here: melting of a solid from solid to liquid through heating, vaporization from liquid to vapor through heating, and the opposite, from liquid to solid, it is cooling by taking heat away, and vapor to liquid, cooling, which is called as condensation, and the reverse of heating, that is called as freezing. So ice to water, water to water vapor. And we also discussed the plot in detail of temperature in Celsius and the time in minutes. Okay, now we discussed that there are certain special temperatures where the as time progresses, the temperature, it does not increase, particularly this ice point, that is 0 degrees Celsius, and this, which is 100 degrees Celsius. Okay, so here the latent heat of fusion comes into play, here latent heat of vaporization comes into play. So at this point, 0 degrees Celsius, solid ice and liquid water, they coexist in thermal equilibrium at 0 degrees Celsius. And at this 2 points, we have liquid water and water vapor coexisting in thermal equilibrium at 100 degrees Celsius. I have discussed it in detail in the discussion related to specific heat, latent heat, and change of state of a substance. So I will not go into detail. Now, I also discussed that there are three important thermodynamic parameters which come into play, which are required to define the state of a substance. You can think of it as the three coordinate points to specify the state of a substance, a material. They are pressure, temperature, and volume. Okay, these three parameters are required to specify the state of a system. Now, what is triple point? So here, if you pay attention, we have this triple point of water. So the triple point of water is a special point, a special combination of pressure and temperature, a special combination of pressure and temperature at which all the three states, okay, all the three states of water, that is ice, which is solid, water, which is liquid, and water vapor, okay, which is the gaseous state. They simultaneously coexist in thermal equilibrium with each other. Okay, all the three phases, okay, all the three phases of water, ice, liquid water and water vapor, they are equally stable and coexist in thermal equilibrium with each other. And that special combination of temperature and pressure is, we have a specific temperature T, which is called as 273.16 Kelvin. We can call it as T subscript triple point temperature, and this specific pressure is 0.46 centimeter of mercury. This is called as triple point pressure, okay, triple point pressure or triple point temperature, or you can also write it as PTR, TTR, TP triple point or TR, whatever choice, you can specify it that way. So we have the triple point pressure as 0.46 centimeter of mercury or 613.2 Pascal, and the triple point temperature is 273.16 Kelvin or 0.01 degrees Celsius. So at these two particular values of pressure and temperature, all the three states, ice, water and vapor, they coexist in thermal equilibrium. So if we understand it, try to understand it with the help of a plot of pressure and temperature, the two values we take, we have taken pressure in the y-axis and temperature in the x-axis. So if you see here, at certain combinations of pressure and temperature, a certain phase, a certain state of water is there. If you take this entire region, okay, this entire region here, this green border line and this red border line, everything that is inside this, that is the solid state. That is, at any combination of temperature and pressure here, let's say we take this combination, okay, this pressure P1 and this temperature T1, it will be solid. Or let's say this pressure P2, okay, this point and this temperature T2, it is solid state. Or this pressure and this temperature, okay, it will again be solid. But as we go in this direction, in this region, okay, here let me use a different color ink, okay, let's say we pick this point which has a pressure of this much. This pressure, let's say we call it P3, and this temperature of T3. At this combination of temperature P3, T3, there will only be liquid state possible. Or any other point here also, this temperature, this pressure P4 and this temperature T4, okay, here also there is only liquid state possible. Then as we go towards this region, here we have only vapor state. Let's say we pick this point, let me use a different ink, this is red, green, let's use blue, okay, let's say we have this point. So we take the pressure, so we have pressure, let's say P5 and temperature T5. So there will be vapor state possible. Similarly, let's say we pick this point, okay, so we have this pressure P6 and this temperature T6. Here also we will have vapor state. So likewise, any particular combination of pressure and temperature, we will have only one state possible, solid, liquid or vapor. But this point, this black dot which we see, okay, which is the confluence, like say three rivers are getting joined at this point, like that is just an analogy. Let's say at this middle point here, this big black dot, this is a special point. This is a special combination of pressure and a special combination of temperature together. So we call this the triple point pressure or the triple point temperature. So at this combination, all the three states, solid, liquid and vapor, they coexist in thermal equilibrium, thermal stable equilibrium with each other. Okay, that is the speciality of this point, this combination of pressure, which is 613.2 Pascal or 0.46 centimeter of mercury, and a temperature of 273.16 Kelvin or 0.01 degrees Celsius. So at this combination of temperature and pressure, all the three possible states of water, solid, liquid, vapor, that is ice, water and water vapor, they coexist in thermal equilibrium with each other. Now, why this triple point is important? Now, we have discussed various thermometric scales, Celsius, Fahrenheit, Romer, Kelvin. There we always pick reference points. Normally, the two reference points, as I said, that are used commonly for designing scales, it is the ice point and boiling point, the melting and boiling point, 0 degrees Celsius, 100 degrees Celsius. But the problem is that any of these fixed points, these conventional fixed points, the melting point and melting point of ice and boiling point of water, they are affected by pressure. Okay, the melting point of ice and the boiling point of water, they are affected by pressure. So any change in pressure can cause a fluctuation in the output, especially when we are designing these reference points to design thermometers, and that can give us incorrect values. So that's why we need a special reference point. So in modern thermometry, triple point of water, that is the temperature of 273.16 Kelvin and pressure of 613.2 Pascal, that is chosen as one of the fixed points, reference points, and this leads to more accurate and precise results. Okay, and presence of impurities also changes their values, the melting point and boiling point, but the triple point is independent of external factors. So that's why the triple point of water is chosen as one of the reference points, fixed points. So here we studied about triple point, which is a special combination of pressure and temperature of 273.16 Kelvin or 0.01 degrees Celsius, and a pressure of 0.46 centimeter of mercury and 613.2 Pascal, at which all the three possible states, solid, liquid and vapor, they coexist in thermal equilibrium with each other. Okay. So we have discussed about triple point of water. So in this video itself, we'll discuss another important concept which is related to that triple point of water concept, that is ideal gas temperature. So we discussed that triple point is a special combination of temperature and pressure, which is pressure of 0.467 mercury and 613.2 Pascal and temperature of 273.16 Kelvin or 0.01 degrees Celsius, where all the three possible states, solid, liquid and vapor, they coexist in thermal equilibrium with each other, these two, temperature and pressure. So what is this ideal gas temperature and how is it related to triple point? So here we have to go back again to Gay-Lussac's law. So here if you see, we have two parameters here. Okay, we have two important parameters that define the thermodynamic parameters which define the triple point: pressure and temperature. So the gas law, which gives us the relationship between pressure and temperature, that is Gay-Lussac's law. So this gives us the relationship between pressure and temperature at a constant volume. So we have discussed it in detail, the Gay-Lussac's law, the pressure and temperature relationship at constant volume, which states that if the volume remains constant, the pressure of a given mass of gas increases or decreases by 1 by 273.15 of its pressure at 0 degrees Celsius for each 1 degree Celsius rise or fall of temperature. Mathematically, this is this. Okay, the pressure at any particular temperature T degrees Celsius is given by pressure at 0 degrees Celsius plus 1 by 273.15 of the pressure at 0 degrees Celsius multiplied with temperature. We can write this as, so here if we specify it, it is basically the pressure at any temperature T degrees Celsius, it is pressure at 0 degrees Celsius plus 1 by 273.15 of the pressure at 0 degrees Celsius for every T degrees Celsius rise or fall of temperature. Okay, so if it is rising, increasing, plus sign, if it is decreasing, minus sign. So here we have considered the plus sign. So because for every rise or fall of temperature, T degrees Celsius, whatever temperature, it will always get multiplied with it. So we can write it as P0 into 1 plus T by 273.15, where we rearrange it, we get 273.15 plus T by 273.15. Now we know that 0 degrees Celsius is 273.15 Kelvin. So this in itself gives us the temperature in Kelvin. So we can write it as Pt is equal to P0 into T by T0, where this is Kelvin temperature. So in a way, pressure is directly proportional to temperature. This is the essence of Gay-Lussac's law. Okay, pressure is directly proportional to temperature at constant volume. Okay, that is the essence of Gay-Lussac's law. Pressure is directly proportional to temperature, or pressure is equal to Kt, where K is a proportionality constant, or P by T is always equal to constant. So if we take a plot of pressure and temperature, temperature in Kelvin, pressure, we will always have a straight line with a certain slope passing through the origin at constant volume. Now we have this relationship, pressure by temperature is always equal to constant at constant volume. So if we keep volume constant, then according to Gay-Lussac's law, at constant volume, the ratio of the triple point pressure and the triple point temperature, okay, this ratio of the triple point pressure, that is 0.46 centimeter of mercury and 600 or 613.2 Pascal, and the temperature 273.16 Kelvin or 0.01 degrees Celsius, that will be equal to whatever combination of pressure and temperature it will be there, okay, any pressure and temperature values. So here we have to determine this T. So we have to determine T. So we'll take T to the left hand side and try to get its value. So T will be equal to triple point temperature multiplied with the ratio of that particular pressure and the triple point pressure. T is equal to T subscript Tr. This is the triple point temperature, this is the triple point pressure. Okay, triple point temperature, triple point pressure. Okay, this is triple point pressure, and this is the particular any random value of pressure. Random value of pressure, random value of temperature. So we have to determine this temperature for this. So triple point temperature is 273.16 and we keep P by PTR as it is. P by PTR. So now there is something interesting which happens. So this temperature, which is defined by this equation, T is equal to this much, that depends slightly on the nature of gas and the pressure ratio. So at low pressure and high temperatures, these real gases, as I said, all gases which are out there, they are not ideal. Okay, they're real. So at extremely low pressures and high temperatures, the real gases, they approach the ideal gas behavior. So if we take this denominator PTR, if we take this denominator PTR and reduce it and take it smaller and smaller to the limit PTR tends to 0, then all the different gas thermometers, there are different types of thermometers, constant volume, constant pressure, constant whatever the parameters that are used, the different thermometers with different thermometric quantities, they give the same value of temperature for a given system. There will be no difference between them. So that temperature, considering we take this denominator PTR, taking it there to the limit PTR tends to 0, that temperature is called as the ideal gas temperature. That temperature defined by the equation is called as the ideal gas temperature on the Kelvin scale and is independent of the nature of the gas. So this ideal gas temperature is equal to limit PTR tends to 0, that is the triple point pressure tends to 0, 273.16 P by PTR. This is called as the ideal gas temperature equation, okay, which closely resembles the ideal gas behavior, because at low pressures and high temperatures the real gases approach the ideal gas behavior, okay, in terms of behavioral characteristics. Okay, so I have discussed this ideal gas temperature along with triple point because they are closely interrelated, and we have already discussed the gas law. So Gay-Lussac's law is already there. So I merged these two topics. Okay, the triple point of water and the ideal gas temperature. Okay, so this is it.